Hey students, so this is our last part in chapter 8 where we finish off our intro to hypothesis testing in our Psych 218 course, that is analysis of behavioral data. So if you remember from our previous two parts where we discussed and went over the steps and logic to hypothesis testing as well as the different types of hypothesis testing, well that is one direction, one-tailed hypothesis test or two-tailed hypothesis tests. And so if we've decided that based on statistical evidence that there is a difference between the sample mean and the population mean, then we would say the results are quote-unquote statistically significant. So one question you might have then is, well, where do you go from there? So you've used this procedure, this inferential statistical procedure to say, oh, there's a difference. That's what we decided upon. And so what next? Well, as you're looking at the slide, the next thing you want to do is to see how big of a difference there is. Of course, you would only do this once you have decided that there is a difference, again, based on the evidence that you would gather, and you would compare the observed statistic with the critical value that you have decided beforehand based on the steps that we've discussed. So what we're looking at then in terms of asking and answering the question, well, how big is the effect or how big is that difference? The answer that we're going to look for is the effect size. As the points say here in this slide, the test itself focuses on the data. It compares an observed value that you've gathered from the sample, with which you'll calculate a sample mean, and then you put that into a sampling distribution that is the null distribution, and you see whether that sample mean is extreme enough in that distribution of sample means for us to decide, yeah, that sample is really different. However, it may not answer the question, is there really a difference? As in, how big is that difference? Therefore, the next point here says a significant effect that is statistically significant is not the same as something that you can call, well, some courses and instructors would say practical significance. Or at least think of it as, well, it may be different, as in the sample mean could be not the same as the population mean, but is it far enough apart even though our statistical test says there is when the sample mean is put into the null distribution? For example, if you have a null distribution that is tall and thin, that is, the standard error is really low, and let's say the mean here is 50, and the standard error here in this case is, and then you transform the 50 into a z-score. Let's say standard error here is only 1. So in that case, you may get a z-score of 2 when you do a two-tailed test of 1.96 as your critical region, your z-score. And so when you decide to reject and you're working with a null distribution that, you know, has a very low standard error, and so you put that back and go, oh, well, it turns out the difference when you look at it, if the population mean was 50 and you transform the z-score back, well, you're not going to get a larger difference. Where if you had a sample of 100 people, and so, yeah, the population standard deviation would be 10, but then you divide a sample size of the square root of 100, then yeah, you would have a standard error of 1. And so with a standard error of 1, a z-score of 2, then if the population mean was 50, then your sample mean would just be 52. So again, if you were to compare 51 to 52, well, that's 2 points away. That may not seem a lot. And again, it depends on what it is. If it was a test, like from 0 to 100, those 2 points don't really look like they make a difference. And that is influenced by the sample size. Whereas in the population standard deviation, a standard deviation of 10 would be, well, oh, wait a minute, 50 to 60. So here you have it in the sampling distribution, that is your null distribution, with a standard error of 1. Whereas in the population distribution, you have the standard deviation of 10. Remember, the standard error is the population standard deviation over the square root of n. So, something to think about. Therefore, it is always good practice to determine the effect size that measures the absolute magnitude of a treatment effect. That is, well, how large is the difference really? And so one technique for us to do when we try to measure effect size is called Cohen's D. And what we're looking for is trying to measure how many standard deviations it is again between the sample mean and the population mean. So in a way, it's quite similar to the z-score for your sampling distribution, but instead of measuring the difference between the sample mean and the population mean in standard error, you're going to divide it by the standard deviation instead. So here's how it would work. Again, remember the example we just had. Let's say we were working with a very tall and thin sampling distribution where the standard error here is just 1. Okay, you could get that with, let's say again, with a population distribution where the standard deviation is 10 and the mean is 50. Here in your null distribution, and we found something that is in the z-score 2, and we decided to reject the null because, well, given that it was a two-tailed test, trying to see if there's a difference. Alpha over 2 at 0.025. So again, a z-score of 2 in the sampling distribution, well then that's only 2 points away from 50. However, in the population distribution, that same 2-point difference is only 1/5 of a standard deviation away. So it's still very close to the mean in the population distribution. And that's what we're looking for in the effect size formula. The technique here is the same as the z-score. We are measuring the mean difference between specifically the mean of the treatment group, the population mean of the treatment group that the sample is supposed to be coming from, and then the mean of the no treatment, which is the population that we're working with. Here the sample would be the treated sample, and then here is the population that is untreated. Well, maybe at least not yet. And then this standard deviation here is the population standard deviation. Again, we're going back when it comes to effect size to the original population distribution that we're working with, not the sampling distribution or the null distribution. And once we've calculated the effect size, again, that would be the mean difference between the treated sample and the population divided by the population standard deviation, not standard error. Then the effect size would have several categories. So if it's between 0 and 0.02, it's not going to be 0. Then we would consider that as a relatively small effect. If If it's about half a standard deviation away, that is half a population standard deviation away, that would be a medium effect. And if it's close to 1 standard deviation away, say a 0.08, then we consider that to be a large effect. Remember, standard error, especially for large sample sizes, is going to be much, much smaller than the population standard deviation, assuming that we're given those values. Like we know what the population standard deviation is and what the population mean is. So that's what we would do. And this is a technique that we would use to determine effect size. So when you do your hypothesis testing, that is in this course, it would be practice questions and test questions. If you have come to the decision that you would reject the null based on your test statistic and it's more extreme than the critical value, then you're going to need to measure effect size as well. And if you have decided to not reject the null, you failed to reject it, the evidence doesn't support your decision to reject, then you would not have a need to measure effect size. So here is a slide that shows an example of how large a difference is for you to say, well, there's a large effect size. So again, one of the major factors is standard error. Notice here, and also standard deviation, from which the standard error is derived based on your sample size. So here you can see in this population distribution where there's a standard deviation of 100, if there was only, a small standard deviation away, like 15 points, 15 points increase in the SAT score here, as it is described, is not going to be very much because, well, if the standard deviation is 100, 15 points is only 0.15 standard deviations away, versus if it was an IQ test and the person has an IQ that is 15 points higher than 100, even though the increase is the same, 15 points, the standard deviation of this distribution of IQ scores is 15, so it's 1 standard deviation away. And so the difference or the effect is much larger. So let's start with a learning check. True-false questions. A. Increasing the sample size will also increase the effect size. And you can think about that in terms of how the effect size, whether that is determined by the increase in sample size and what the sample size influences in the sampling distribution. B. Larger differences between the sample and the population mean increase the effect size. Again, you can think about that as well. The difference between the sample mean and the population mean. Here, the sample is the treated sample. Now, something to keep in mind. While sample size affects standard error because it's part of the calculation of the standard error, for effect size itself, it doesn't, because when you're measuring effect size, here as Cohen's D, so here we got standard error, which is directly influenced by sample size because it's part of the denominator. But for Cohen's D, you have the sample mean, treated sample, subtracted by the population mean. You're trying to find the difference between them. And then you have standard deviation of the population. Now remember, the standard deviation of the population does not involve sample size at all. So you would have the sum of squares, and that's the whole population, which somehow we're given. And divided by big N. And this big N here is not the sample size. Notice sample size has lowercase n. Population size has capital N. So Cohen's d is not affected by the sample size at all. It does affect standard error though. And for B, yes, looking at the effect size and how it is measured, yeah, a larger difference between the sample mean and the population mean would result in an increase in effect size, regardless of the standard deviation, provided that if you're comparing two distributions with the same sample standard deviation of the population, and then the difference in the means change. Again, a larger mean difference here would be a larger effect size. So the last bit of our lecture recording today is going to talk about statistical power. So if you remember, there are 4 outcomes based on the 2 decisions we make in 2 situations where either the null is true or the null is false. And we could decide to reject the null or fail to reject the null. And if our decision matches what happened on test day, that is the situation, then our decision is correct. And one of these correct decisions is a true positive. That is, the test has quote unquote successfully detected a difference when there is a difference. And this probability of us correctly detecting a difference is called statistical power. So here then, to review, and you can draw a decision matrix for this. So again, you got your situation, and you have your decision. So I'll quickly review here. So again, if the null is true, you're supposed to fail to reject it. So that's correct. If you reject the null when the null is true, well, that's type 1 error. And the probability here is alpha. Whereas if in that same distribution, the null distribution, when the null is true, assuming that the null is true, failing to reject it would be a correct decision. Therefore, it's 1 minus alpha. Here in the other situation where the null is not true, again, you're supposed to reject the null because, well, there actually is a difference, and your statistical test is supposed to detect that. So this is correct. The other decision, which is not correct, when the null is false, that there is a difference on test day, and the test has failed to detect the difference, leading you to fail to reject the null, then that would be the type 2 error, a false negative. And that would be beta. So power then here is the remaining outcome and the remaining probability in the alternative distribution. That is not the null distribution. That would be 1 minus beta. One thing to note here, and I'll say this first, and it will make more sense in the next slide where we work with distributions, is that there is really only one null distribution. Just like there's really only one value that matches the population mean exactly, and that is the population mean. So if the population mean is 50, well, the only value that matches that would be 50. Whereas any other value would be different. And therefore, while there's only one null distribution, where the mean of that distribution would be exactly the population mean, the alternative distribution could be any other number that you expect the treatment to have. So if you expect the treatment to increase, I don't know, IQ by 15 points, if that's what you're expecting, the alternative distribution, based on what your research is predicting to do, predicting the test to do, or whatever the effect is, then the alternative distribution you're working with would be 15 points higher than the mean. And then that distribution would have sample means around that increased mean. That is, well, 115, for example. Whereas the null distribution would have sample means around 100. So power here, this probability exists in the alternative distribution. And remember, there are multiple possible alternative distributions determined by which one, how you predict the effect to be. Well, if it's 15 points above, well, that's its own alternative distribution. If you expect a 5-point difference, then that would be another alternative distribution. That would be actually closer to the null distribution. So for example, your null distribution, let's say the IQ is 100 points. Well, that's the population distribution with a standard deviation of, let's say, 15. Okay, so you can have your null distribution, for example, and let's say I'm using a sample size of 25. So therefore my standard error would be 15 divided by square root of 25, which is 5, well, 3. So this would be one null distribution. Whereas if I predict a 5% increase, well, then I'm not going to draw these overlapping because it'll be hard to read. But then it would have a mean of 105 because you expect that treatment, whatever it is, to increase IQ by 5 points. And then because we're working with a supposed, treatment effect, then the sample from which that treatment is supposed to be, conducted, then you would have its own sampling distribution where you assume, well, in this particular case, the alternative hypothesis is true. Here, that is specifically the treatment would increase everybody's IQ by 5 points. It would have the same standard error as the null distribution because the sample is the same size, but the mean location is now different, and because you're supposing that, yeah, this treatment really works for everybody and that sample is really just, from that population, therefore the means would now gather in the alternative distribution around the mean value. So if you predict an even higher increase, let's say 15 points, so then a new mean would be 115, and then this would be another alternative hypothesis. So I might change that from H1 to H2, for example. Usually we just make one prediction. You wouldn't go around making multiple predictions. But I'm just doing this to show you. Same standard error again because you're using the same sample, but your prediction's different. Therefore, whatever you predict, it would have its own alternative distribution. Now, power is usually estimated before starting the study for two reasons. One, you made your prediction. You would predict how large the effect would be. And two, calculating the power of a test would help you determine how large the sample you would need. Again, your sample size directly influences standard error, which is the standard deviation in your sampling distribution, which would change the shape of your null distribution as well as your alternative distribution, depending on what your prediction is. That is how far you think the mean would change, positive or negative, away from the population mean. That would predict how large the treatment effect is. Now, in this course, we would not go into specifically, or at least in this chapter, specifically how power is calculated, but the textbook does talk about it, and the process is not too hard as long as you know how to change a raw score, or in this case a sample mean, to a z-score in the null distribution, and then convert that into another set score in the alternative distribution, and then figuring out the proportion in the alternative distribution, well, how much of that area would you be making the 1 minus b decision and outcome. So here's an example of this. You got your original population here with a population mean of 80 and, population mean of 10. Wow, this is a typo over here. Population mean of 80 and a standard deviation of 10. Okay, if the null is true, if there's no treatment effect, well, it's the same thing. However, if the alternative, your prediction is true, then everybody that receives the treatment would have a new population mean of 88. 8 points difference, increase. But the standard deviation would be the same for now. So then how we're going to test this, again, we can't ask everybody, so we would collect a sample. And again, your sample size here is going to affect the power of your test. Again, think about this in terms of standard error. The larger the sample, the tighter your that is taller and thinner your sampling distributions would be. Remember, the null distribution is a sampling distribution of means, and so is the alternative distribution. These are two different distributions with the same standard error, but the means are different. This null distribution has the same mean as the population mean. This alternative distribution here, which I'm going to label as mu m1, is not the same anymore. It's going to be plus the effect, whatever the effect is. In this case, it's plus 8. Now notice we will apply what we learned in step 2, where we set a critical region. So again, we set alpha, and that again is arbitrary. We set this in the alternative, in the null distribution, not the alternative. So we can set our alpha. This is a two-tailed test, so we split the alpha in half. And so in this region and everything above it, we reject the null. Same with this side. We reject the null on the opposite extreme. Everything in the middle, we fail to reject. I'm going to use shorthand. So this shaded area in the null distribution is kind of what we're expecting. So in the alternative distribution, let's say the researcher predicts a 8-point increase, which is really far away. And our critical region in the null distribution has been set with a critical value of plus 1.96. That is the z-score. Then this corresponding value, and this is the fun part, the standard error of the null distribution is 2. And this value here is, the critical value is 1.96 standard errors or standard deviations of the null distribution away from the mean. So again, if we want to solve for x here, the new sample mean actually, solve for m, then the critical m value, so we would have, well, we can review. So the z-score here for your means well, it's the sample mean minus the population mean divided by standard error. So in this case, well, we can solve for the sample mean. So we can do this with algebra. So we're looking for the m. So it's the z-score multiplied by the standard error plus, well, in this case, I can put the population mean first. Makes more sense. Plus the multiplier. The standard error is the multiplier of the z-score, is the multiplier of the standard error. How many standard deviations away? So here we can say, okay, well, we know the population mean is 80. Okay, it's 1.96. times the standard error, which is 2. Well, it's 80 plus 3.92. So therefore, the critical value of this mean is 83.92. So that's this point right here. So to calculate power then, this is the point where if a value is more extreme than 83.92, that is the sample mean, that corresponds to a 1.96 z-score in a positive direction in the null distribution, then yeah, our decision would be to reject the null, and in the alternative distribution, assuming that it's true, then what is the probability in the alternative distribution? Here is the null distribution with its own probabilities using alpha, and in the alternative distribution we use beta. So again, in the alternative distribution, the error would be, well, the null is not true. Yeah, when the alternative is true, the null is definitely not true, because there is a difference. Although again, as a reminder, there are multiple possible alternative distributions depending on what your prediction is. But when the alternative distribution is true, no matter how far away it is from the null distribution, then it is no longer the null distribution. The null is no longer true. So there is a region in the alternative distribution. Usually it's much smaller than the power, depending on how far the alternative mean is and what the shape of the standard error is in the alternative distribution. So here, this would be beta, as in the wrong decision, given that the alternative is true. Because, well, we say there is no difference when in the alternative distribution there actually is. So the rest of the shaded area here then is 1 minus beta, which is power. And so you can calculate power here in the alternative distribution once you figure out what the z-score is. So notice here, it's the same shape as the null distribution with the same standard error, just the mean is different. Here it's 88 instead of 80. And so we want to find the z-score then. Of 83.92 in the alternative distribution. So the mean is different, but everything else is the same. And so you would get, okay, negative 4.08 over 2, and therefore it is negative 2.04. So that's your other z-score. So then you would look up your unit normal table for negative 2.04, and we have already determined which part of the distribution we're looking at because we labeled it. We want power, which is the body of the alternative distribution, 1 minus beta, and so we're looking for a big portion, 2.04. Well, yeah, according to your unit normal table, it's 97%, almost 98%. So this area right here is actually 0.9792. Let's double check. 93. And so again, depending on what your prediction is of the treatment effect, and also depending on your sample size, the statistical power changes because the shape of the alternative distribution changes. And the proportion within which your critical region is placed in the alternative distribution is going to change as well. Again, depending on your sample size, the proportion would be either larger or smaller. And so we're going to explore this more when we talk about influences on statistical power, which is the next slide. So here it is in point form. Again, as the mean difference increases, that is effect size, power increases. Makes sense. As sample size increases, power also increases because the standard error is greatly reduced, and so the distributions, both the null and the alternative, is going to be taller and thinner, and therefore it would make the test easier to, well, it would be more likely for the test to detect a difference. Furthermore, using a one-tailed test is also going to increase statistical power relative to a two-tailed test because you are decreasing the critical value, and in the alternative distribution, and I'll show you this, I'll make the distribution shorter and flatter to show you. So the left distribution is the null distribution. The distribution on the right is the alternative distribution. Each has its own mean. But the standard error is the same. So the standard error is the same, but we change the location of your critical values. If it was a two-tailed test, it would be 1.96 if alpha was 5%. But if we make it, and so this region right here would be power in the alternative distribution. But if we change the test, you would do this beforehand, if we change the test from a one-tailed test to a two-tailed test, again, you might justify that by saying, well, I've made my prediction, I know what the direction is going to be, or I strongly believe, based on evidence, most likely, that, yeah, I would expect an increase rather than a decrease. So you would use a one-tailed test, and so the critical value for a one-tailed test, if alpha is set at 0.05, 5%, would no longer be 1.96, but 1.645. Therefore, because the critical value is closer to the left, that means you're going to have a larger body portion in the alternative distribution. So I'm going to double shade this part. So notice the difference. Again, the further to the left you set your critical value, that is you increase alpha, you're going to also increase power because your test is going to detect a difference, or say there is a difference, more of the time. Conversely, ways to decrease statistical power is to reduce the alpha level. Usually this is not just whether, changing a one-tailed test to a two-tailed test. Again, the reasoning would be, well, if you're just trying to see if there's a difference, you would use two tails. If you have evidence and reason to believe there is one direction in difference, then you use a one-tailed test. Here we reduce alpha level by changing the whole alpha level. So instead of 5%, we use 1%. Therefore, if we decrease alpha, we increase the value of the critical value. And so instead of 1.96, for a two-tailed test, the same two-tailed test of an alpha of 1%, again, the alpha will be split in half. Well, that would now be actually a lot higher. The Z score would be 2.575.